So I will illustrate how to apply conservation of linear momentum principle. First, you need to choose your system. First, you need to choose your system and then confirm no external force, and then you can apply it for the system. This is our system. Surface is smooth. Though vertical direction is not of our interest, still vertically there is no net force. Gravitational force is cancelling the normal reaction. So F external is 0. So momentum should be conserved. When we say momentum, it has three components, x, y, and z. But since this motion is taking place in one direction, you don't have to worry about y and z. That's the direction you should choose for momentum conservation, this direction. In this direction, momentum is conserved or Px is conserved. Px. I think x itself tells the direction. Px is conserved. So Pxi equal to Px final. What is Pxi? Mass of the block into 20 on the right side. Right side I am choosing S plus X. Final, we will have to consider both fellows, M1 V1 plus M2 V2. Let's say one of them V1 or V2 is 30. Of course, mathematics will take care of this thing. I mean, the greater speed must be on the right side. But M1 is equal to M2. Can you solve for V1? (10 meters per second). Any questions? Let me know. The first thing, your system. What would you choose your system? I'm giving you three options. A, B, and C. And maybe the fourth option other. Fine. That choice is correct. So when the hero hits that car, then there is going to be some force that this man applies on the car, and car will also apply some force on this man. But then those forces will be internal forces, and they don't count in this law. Once system is decided, check for ext, fext. In this direction, since car was going with a uniform velocity, we assume no force was acting in horizontal direction also. And therefore, in that direction, we can apply CULM. For the system, for that direction. M into V, for that direction, this M into 0. This man is falling vertically. He doesn't have any horizontal velocity. Finally, now you would expect that the hero will get himself attached to the car. So M plus M. And jointly the car has some speed. Any questions? Let me know. We are of course ignoring that the driver would have accelerated. We are ignoring all that. Sometimes in place of speed, kinetic energy is given. So it becomes important to get the expression for momentum in terms of kinetic energy. That's very easy to get actually. Suppose kinetic energy is given in place of V. K is given. So you would say K is half mv square, and therefore V is this, and therefore P is this. Which is this. Now try this problem. One is to 2 is the correct answer. If you would like this to be discussed on the board, then raise your hand. Note that momentum is a vector, so if momentum in this direction is 2 unit and momentum in this direction is 2 unit, and if we are talking about the same thing, then change in momentum would not be 2 minus 2, which is 0. It would not be that, because you can't subtract numbers without considering direction. So if you want to subtract, you must go for vector subtraction. And when you write PF, it will be 2 unit towards the left. If I say x-axis is on the right, then left will be minus I. This fellow is on the right side, x direction, I cap. So actually change in momentum is non-zero, 4 units. When a ball hits the wall, and ball is your system, then momentum will change. A ball is your system. Because there is external force. When the ball hits the ball, wall applies force on the ball. And if ball is your system, then this is an external force. So momentum is bound to change. So when light hits some wall, then if we use the particle theory of light, imagining light as stream of particles, then light bounces, these particles bounce, and for each particle there is change of momentum taking place. And when there is momentum change involved, there is force involved. You know, Newton's second law, rate of change of momentum is force. Will momentum change? Will momentum not change? That depends on your system. If in this problem If in this problem I take the system as man, as a hero, will his momentum change or will his momentum not change? If the system is the man, then look out for external forces. Now, when the man hits the car applies force on the man. Now, is that internal force? No. If man is your system, how can that be internal force? If man plus car is your system, then that force is internal force that the car applies on the man, because they were treated as one system. So what will this hero say? This hero will say that my momentum has changed. I was going in y direction, negative y direction. I was going in vertical direction. Now I am going in horizontal direction. My momentum has changed drastically. That's what this hero will say. And the car will say, well, I was going at some velocity, and now I am going at reduced velocity. V dash is how much? M over M plus M times V. This is a decimal multiplied to V, decreasing V. So the car says, because of this fellow, my speed is reduced. I lost momentum. So the hero says my momentum has changed, car says my momentum has changed, but together they say that momentum has not changed. So will momentum change? Will it not change? The key is the system. That's the key. Now I was talking about this type of situation. You hit the ball on a glass and the glass breaks. Ball hits the glass and the glass breaks. That's because there is momentum change involved here. And rate of change of momentum is force. So because of that force, glass breaks. Light can also apply force. Light is made of particles. For various phenomenon, light is to be treated as particles. Light is to be treated as made of particles for various phenomena. And for them, momentum principle works. So laser gun, any stream of light particles are called photons. But in case of light particles, momentum is not given by mv. Momentum is given by mv in classical physics. We have been doing classical physics. So that their momentum is mv. But in the quantum world, when you are dealing with light, and light is to be considered as particle, then the formula for momentum is different. This momentum principle works at quantum level also. Now we got conservation of linear momentum principle from center of mass concept. Center of mass. We took M1, M2, M3, M4 as masses. And then we arrived at conservation of linear momentum. You would not see any M when you are dealing with photons. Photon is particle of light. And when you deal with particle of light, you don't use M for mass. Then mass is not mentioned. Momentum of photon is h by lambda. H is Planck's constant. Lambda is the wavelength of the light. So even color, different color of light of different color will have different momentum. Blue and red color travel at the same speed. But if blue color light hits glass and if red color light hits the glass, who is more likely to break the glass? Momentum is h by lambda. So if lambda is less, p is more. Who has lower wavelength? Blue color or red color? Lower wavelength. Red has higher wavelength. So blue color has lower wavelength. That means blue color will have higher momentum. So in a case like this, blue color is more likely going to break the glass than the red color. Blue color also has more energy, as you must be knowing from Bohr's model discussion. So conservation of linear momentum works at subatomic level also, quantum world also. In that world, there may be some particles whose masses are to be considered. For example, electron, proton, and some other particles are also there. There are too many particles besides electron, proton, and neutron. The search for particles never seems to end actually. Antineutrino, neutrino, positron, there are too many of them. In some cases, you would use mass. For electron, you would use mass. Positron, you would use mass. But for anything which is like light, anything which is like light, that includes X-rays, alright, there was slight interruption. I was saying that in case of something like light, for example X-ray, any electromagnetic ray that we talk of, whether it is X-ray or it is some radio ray, microwave, anything of that type when we deal, then this is what you need to use. H by lambda. Anything which is light-like. Momentum formula is h by lambda. Anything which is having mass like electron, proton, neutron, for them momentum is mv. And when we combine these two fellows, light type of behavior and electron or proton type of behavior, even then conservation of linear momentum is applicable. For example, you have learned from Bohr's model that when electron jumps from second orbit to first orbit, then light goes out. right? Second to first, then light goes out. Now you would have momentum consideration. Now you would say, okay, I have atom as my system, and from my system, light is coming out, which means photon is coming out. And then you would say that in my system there was no external force, so the momentum should be conserved. So atom should bounce in the opposite direction. So if a photon comes out from some atom, and if photon goes to the right side, and photon has h by lambda momentum, then just like bullet going to the, if bullet goes to the left side, gun must go to the right side. If photon goes in one direction from the atom, atom must go on the other direction. Just like that. And when you use momentum for atom, then you would use mass, m. Atom means mass. And when you are using momentum for photon which has come out from the atom, you won't use mass. Photon's momentum is h by lambda. We don't talk about mass for photon. Photon is energy. Energy of photon is h nu. Length constant times frequency, h nu. Energy of photon is h nu. That is not kinetic energy, that is the energy. Right? So photon has energy which is h nu. You should not call it kinetic energy, it is the energy. And photon has momentum which is h by lambda. And when you deal with such phenomenon where particles with mass representation and particles without mass representation both are involved, then for particles with mass representation you would use mv for momentum, and for particles without mass representation like light particles, type of particles, you would use h by lambda. Okay, I hope it is clear enough. And theoretically speaking, you can break glass using light, theoretically speaking. And maybe practically it should be possible one day. So it's basically like hitting the ball to the glass, and the ball bounces back, and it breaks the glass also, just like that. So in such case, you would say that for the ball system, momentum has changed, right? But for ball and the glass system, momentum has not changed. That means whatever change is taken place in the ball system, same change must have taken in the mirror system, glass system. You get that point? If the total change is 0 in ball plus glass system, if in ball system momentum change is x, then in the glass system shouldn't it be minus x, so that the total becomes 0? So if momentum changes for the ball system, then momentum is imparted to the glass system, and that's why it breaks. Because force is rate of change of momentum. You learn law of reflection at quite an early stage, and it may look pretty obvious that angle of reflection should be equal to angle of incidence. That's not necessary. That's necessary for light, which is what you learn it for. But as a general law of nature, it doesn't have to be true. I hope in some problem we will deal with this situation. But I will give you an idea right now. In some surfaces, when collision takes place, some energy is gone. When I say some energy is gone, mechanical energy. In those surfaces where mechanical energy in some part is gone, angles don't have to be equal. You can make note of this point. In case of light, this of course is not valid, and that's why you get angle of incidence is equal to angle of reflection. So this law should not be taken for granted for mechanical collisions, ball colliding with surface. Should not take it for granted. You should remember that if mechanical energy is conserved, then yes, it is true. These two angles will be equal. If mechanical energy is not conserved, then these two angles don't have to be equal. Anyway, in this problem, question says that angles are equal. So if it is 45, then this would be 45. Right? Then magnitude of change in momentum of the ball. You are interested in the ball. So ball is a system. So momentum vector has this direction in the beginning, pi. Pi vector is in this direction. And pf, whatever is the direction of the velocity, same is the direction of momentum. So that's pf. pf, pi. With the same speed. With the same speed. Now with the same speed means magnitude wise these two vectors are equal, isn't it? Same speed. Now tell me, if this is mv and this is mv itself, the same v, option A, answer should be 0 for part A. Option B, answer should not be 0. What do you choose, A or B? Answer is B, because momentum change is a vector subtraction, not a scalar subtraction. Otherwise, mv minus mv is 0. But it is not mv minus mv. It is mv with this direction. It is this mv with this direction. When you want to subtract vectors, you can take components. So this mv will have two components. One here and the other here. mv cos theta. Whether I say sin theta or cos theta, if theta is 45, it would not matter. mv by root 2, mv by root 2. This pi will have two components. This angle is 45. This angle will be 45. So again, same story, mv by root 2, mv by root 2. Now, you want pf vector minus pi vector. When you subtract vectors, you can subtract their components. Look at this and look at that. What is the difference? 0. So pf minus pi is effectively this minus that. Two vectors in opposite direction, when you subtract, they actually add. So mv by root 2 in this direction minus mv by root 2 in that direction is 2 times mv by root 2. And that would be in final this direction, final minus initial this direction. That's the momentum change. This is delta p vector, which is pf vector minus pi vector, delta p vector. It should be, yes, minus and plus is okay. The minus will only tell the direction convention. I'm showing this direction. In this direction, answer would be root 2 mv, root 2 mv in the left direction. Direction I've already shown here, left. So delta p is root 2 mv to the left. Now just put the numbers and see if you are getting 0.14 SI unit. Okay. Well, if you are saying minus, then I suppose you have taken x direction on the right side. So that's why you are giving negative answer. If I say on the left side it is root 2 mv, then I should not be saying on the left side it is minus 0.14. The answer should be left side just 0.14 or right side minus 0.14. So if you are saying minus 0.14, you are saying it on the right side. On the right side minus 0.14, or left side plus 0.14. Any questions, let me know. Or we go to part B. Okay. The change in the magnitude of the momentum of the ball. Change in magnitude of momentum. That means pf vector mod minus pi vector mod. That should be very easy. What do you think should be the answer to this? That's right. That's right. Magnitude is mv. Magnitude is mv. No change in magnitude. Any questions? Let me know. Now since it is light, certainly angle of reflection can be used, theta theta. The math is just like this. So I think I shouldn't be doing this here. I should rather be giving it an assignment problem. This is P, that is P. Only one option is correct. Only one option is correct. That's good. Now, when the bullet hits the block, then block will acquire some speed. Because the surface is smooth, the block will have to acquire some speed. Linear momentum of the block has to change. Bullet plus block system, linear momentum would not change. Bullet plus block system, but for block alone, yes, it will change. Block had 0 speed, now it has got some speed, kinetic energy will change. Height is not changing. C is correct. Temperature of the block. Now, this you can answer from common sense, or the technical answer would be that final energy, kinetic. Technical answer you will get when you do this math. Bullet, mass, speed, applying COLM, mv equal to m plus m v dash. So the speed of the system would be this much. Just find out this. You will have to do this math. Half m plus m v dash square minus half m v square. Kinetic energy final minus kinetic energy initial. There is no potential energy change involved. Height is the same. So you will know from this math that the kinetic energy is changing. That's what you will find when you put this v dash here. When you put this v dash here and you simplify it, you will find that there is certainly change in kinetic energy. So that math you will have to do. And then you will wonder, why should kinetic energy change? And the answer is, can you guess? Why is the system losing kinetic energy? Any answer? Friction. Friction is not wrong, but not clear answer also. Which friction are you talking about? That's a clear answer. That's it. So when the bullet enters the block and travels inside the block, it rubs with the block. That friction is eating some kinetic energy. And that's why the temperature of the block and the bullet also. Bullet will become hotter, and so will be the block. So will the block. I've already given you the assignment. We stop now.